So thank you very much. Thank you to all of you, and especially to the organizers. So this is a little bit the outline of what I'm gonna talk about today. So first, I will kind of make it clear what I mean for in-plane chirality in this tantalum disulfide. Then why is interesting actually, which means how can we control it, and by which means. We tried several things. Then I will move to a very old problems that always pop up in this kind of materials where you have got distortions and correlations, which means is it a Mott or Peyer's scenario more adapted, or eventually both. And finally, I will show you that after photoexcitation, the electronic bands becomes flat, and electrons becomes initially localized into David stars. Okay, let's start from the beginning. So the structure, you saw it before, although this is probably only the second or first talk about this material, but you already saw that this material is a trigonal antiprismatic structure. And already at room temperature, it developed a large charge density wave, forming this kind of clustering in David star shapes of the tantalum atoms. Okay, the crystal would be space group D3D if you wouldn't have these clusters. And that means that you do have three mirror planes in this case. And what happens when you form the charge density wave is that when you reduce the space group, you go from D3D to C3I, and you lose basically the three mirror planes. So we call this in-plane chirality, although it's a little bit of an abuse of language, because such space group is centrosymmetric, so it's not really a 3D chiral material. So what does it mean having this in-plane chirality is the following. You take here one of these mirror planes. When you do a clustering, these mirror planes is no longer a good symmetry. Why? Because you have got that the superlattice unit cell is tilted compared to it, and it could be tilted either towards the right, and then you have got an alpha configuration, or towards the left, and then you have got a beta configuration. Sorry, I wanted to go back. Clearly the best way, or most so to say direct way, let's say, to see it is just by doing STM. This is, for example, the case here. You have got two STM images showing you the two configurations. Of course, if you can see it in real space, you can see it also in reciprocal space very easily. So if you do a lead on this material, if this is the mirror plane, the broken mirror plane, you would see that superlattice peak are tilted counterclockwise by 13.9 degrees in the alpha configuration, and clockwise still by 13.9 degree in the beta configuration. So there is a very easy way to check it, that is just doing a lead that is even easier than doing an STM image. Okay, another way how this in-plane chirality gets imprinted on the properties of the material is in photoelectron intensity maps. So if you took now here constant energy cuts, these are, in this paper has been shown, a different energy from the Fermi level 0.1, 0.3, 0.5. You see that there is a winding related to this in-plane chirality, and here is a little bit less direct to understand it. In order to understand what you're seeing, you need some DFT simulations that reconstruct the spectral weight distribution in the extended zone scheme. But if you do it, as has been done here, you can very easily see that the agreement is pretty good, and the assignment is clear. So this has been seen in many papers before, but probably only in this paper has been discussed extensively for the first time. Okay, and the third, probably even the most interesting thing is that even if, as I say to you, the material has not linear dichroism, because it's not really, it's centrosymmetric, it cannot have linear dichroism, but it has a very peculiar Raman response. So you do have some dichroism if you take a look at the Raman scattered light. So, for example, for the AG modes, you should write the Raman tensor in this way. And you may see that you have got two here non-diagonal terms, and it's complex. It's complex because light get absorbed here quite a lot. It also get diffused when you get Raman, but you are really absorbing a lot of light. And then if you just sandwich this Raman tensor between a light that is circularly polarized sigma plus incoming, and you take a look at the light that is scattered with sigma minus, you would see that the intensity, it depends on this angle alpha, and the dependence goes as minus 2a sinus alpha. Of course, you can swap the two polarizations, so you come with circularly polarized sigma minus in, and you look at the scattered sigma plus, so you permute these two, and in this case, with minus signs get from minus to plus. And this is a huge effect in the Raman spectrum. So the contrast, it's really, I would say, impressively high. Okay. So there is some kind of dichroism also here, although it's not the linear dichroism. You have to go to the Raman response. Okay, well, you would say to me, what's interesting in that, since it's kind of a space group that has got this kind of in-plane chirality, you may have many of them, and what's particular about tantalum disulfide or about this compound? I would say what is particular here is that the chirality is not related to the main lattice structure, but to the charge density wave. And what does it mean? It means that eventually you have got many ways to control it. Why? Because charge density wave can slide, can be deformed, can make a glassy face. So they are somehow more ductile than a usual lattice. And this is exactly what we were looking for, trying to control this charge density wave. And I will show you several ways we managed to do it. Okay, the reason why, indeed, it's kind of easier to control it in this charge density wave system than in a simply structurally distorted material is that here you can easily form in this so to say, clustering of David stars, domain walls that are metallic. So this is, for example, simulations of atoms coming from this paper here. They simulated the STM map, and then they could get a very good agreement with what is seen in, for example, a phase that is called the nearly commensurate one, where these domain walls get activated thermally. Actually, you can activate these domains thermally. They can form an honeycomb structures, as you see here in the nearly commensurate phase, or they may even form a striped structure. I would say the domains have been characterized very well in this case, not really in this case, most likely, maybe there is not a big difference between the two, but it's something that has never been explored really. Okay, but the punchline here is that these domain walls do not cost a lot of energy. They cost typically 10 to 30 millielectron volt nanometer to be formed. And then this gives us an end to really try to change the chirality by making use, in a certain sense, of these domains. Yes? Yes. Or typically the entire crystal. It's almost monodomain. Yeah, yeah. I would say it's quite hard to Not always. If you've got cracks in the crystal, you may find indeed regions with different alpha and beta, but if you've got so to say, a well-defined bulky crystals with not many cracks, typically is monodomain, yes. This domain walls is because when you warm up, for example, the system, what happens is that automatically you create a discommensuration between the superlattice and the main lattice. And this discommensuration, so it's a nearly commensurate charge density wave, automatically form metallic domains. But are here, you would say, is nearly a commensurate phase. Here looks also very near to a commensurate phase. And in between here, you do have thermally activated domains. Yeah? So it's just a different phase, but it's nearly commensurate in which, yes?
Just to be clear, these are not domains between different chiralities.
No.
This is just a wave vector mismatch.
Yes, yes, wave vector mismatch. Yeah. Okay. And indeed, this has been shown many, many, many times. It gives the richness of this phase diagram because when you are very high temperature, okay, very high means 360 Kelvin, you are in this incommensurate phase that is not chiral at all. Then the system go nearly commensurate, where you have got the formation of David stars that gets nearly commensurate to the lattice, but you still have these metallic domain walls, like here on the blue line. If you cool down below 180, you enter in the commensurate phase. When you heat up, you see the big hysteresis at 220, roughly 220. You enter in this stripe phase that is slightly different from the nearly commensurate one. And then only after, at how much it is, 260 probably, you are back into the nearly commensurate phase. So you see already that just by changing temperature, you have got a very rich phase diagram. So the first thing that you have done is basically to sit here in the commensurate phase and try ourselves to take a look whether with photo emission we could get a hint of which was the chirality of our sample. And it's very clear. I mean, you see here kind of a winding in the spectral weight that has been acquired in the C phase at binding energy of 0.5 eV. So this is a constant energy map. And if you do DFT simulations, the agreement, I would say, is good enough not to have any doubt about the fact that we are in the alpha configuration. You move on the sample on several spots, you always see this. As I say to you, is very uniform. This will be almost always the case. Okay, you can also do some cuts. For example, in this direction here, or this direction here, the direction of the arrow counts. And now I plot wave vector towards energy. It's even easier to see that in one case and in the other, for alpha chirality, you do have a piling of spectral weight a little bit more towards the right, as predicted by simulations. Okay, and this was kind of a little bit the, so to say, in a certain sense, the first surprise is that when we go from the C, so commensurate charge density wave to the stripe one, and then the nearly commensurate, we see what? We see that the chirality change. So it goes from an alpha one to a beta one. So the first time we saw it, I thought it was pretty unexpected. So we have done many experiments in order to, so to say, confirm that this is the case. Of course, for example, if you see it in photo emission, you should see it also by doing lead, as I said to you before. And this is indeed what happens if you hit very slowly and you acquire a lead pattern. Here you are in the alpha phase. Then in few degrees you have get this mix of alpha and beta phase, and then you switch into the beta phase. So the lead is really very telling. And here just I show you a little movie. So here we are alpha, and then you will see that it switched to beta. So the several images are different temperatures while we were increasing the temperature. Okay, good. Finally, of course, I say to you that Raman is a very powerful tool in order to assess the chirality. And for us, it was important because the main question is this switch happening only at the surface? Photo emission is surface sensitive, lead is surface sensitive, or is happening also in the bulk? And Raman is way more bulk sensitive. So we did Raman, and you see that also in this case, when you do the dichroic constant, so basically you subtract the intensity of sigma plus, sigma minus to the sigma minus, sigma plus, you can clearly see in this dichroic contrast that you have got, sorry.
What is the difference between left and right?
So here we are cooling down, and the transition takes place at 180. And you go from the nearly commensurate phase to the commensurate one. And here you are heating up. And then you go from the commensurate to the T phase, and nothing happens when you go to the nearly commensurate phase again.
So this is the hysteresis that you showed?
Yes. This is exactly the hysteresis that I do show. So it's which, either if you go down or if you go up. And now the question is, how does this happen? So the process is probably quite complicated because what happens is that you have got clearly a double well, so to say, if free energy, if you're thinking about an order parameter that defines the chirality in the nearly commensurate phase, and similarly in the commensurate one. And when you do the transition, so you are just slightly changing the commensurability. Here we are almost commensurate. Here we become completely locked in commensurate. And what happens is that actually the system prefers to go from this minimum to this minimum instead of going from alpha to alpha. And same thing when you were commensurate before here and you heat it up. Well, for some reason here the activation path it's such that is favorable to switch chirality instead of maintaining it. So in order to see that this is at least feasible and not completely crazy, okay, beside the fact that the experiment is not really doubtful, it's to show that if you create metallic domain walls between alpha and alpha, as we did here, you relaxed a unit cell of 1,016 atoms, or you do the same but with alpha beta chirality and still metallic domain walls, well, the energy that you cost is very similar. So although I cannot tell you exactly what's going on, I can tell you that from an energetic point of view, this chirality switch is not totally unlikely, as you may see. So there is a way that we can control it. How to do it, for example? The first is by thermal gradients. So the first very easy experiment that you can do is that instead of having a Raman beam that does 2 milliwatt, you crank up the power of your Raman beam to 10 milliwatt. And if you do that, you would see that the transition is no longer at 180 on this graph, but is at 170. What is this? This is simply due to the fact that we are actually eating up locally with our Raman beam the sample. So in the focus of the Raman beam, we are eating up by 10 degrees. So we are making thermal gradients. Well, if you make thermal gradients, nothing happens anymore. So you see, this is a very subtle, so to say, phenomenon, and that can be very easily, so to say, changed by experimental protocol or parameters.
Sorry,
Yeah.
one thing I'm confused about. So before you were saying that you can get either alpha or beta domains, and usually the whole crystal is in that particular material. That applies to the high temperature. So if you
No, you mean in the simulations, you mean?
Well,
Or,
from the very beginning when you were saying,
the very beginning is everything alpha or everything beta?
but is it dependent on the temperature or no? At a high temperature, you so
It depends on the history. Let's say we have done it several times, these things. So for example, if you make thermal gradients and you go through the metal insulator transition, you almost never switch. And if you be very careful not to have thermal gradients, and you also need very good crystals with not internal strain, then you almost every time switch. So you may decide whether you want to switch or not at the metal insulator transition.
they also start from the beta phase and then going to the alpha.
Yes, of course. Completely. So you can go from one to the other, and you decide whether to go or not. For example, by putting a laser beam, or another things that you can do to pin the chirality switch is by going fast. If you before we were changing the temperature at 25 degrees per hour, now we go at 80 degrees per hour. By just going down very rapidly with your, so to say, open cycle cryostat. And you would see here that the chirality, in this case, let's see where it is. Here. You will see that there is a transition, but the chirality doesn't change. Okay. Now, indeed, we have done some statistics. And if you are very careful not to put any thermal gradients, let's say 14 times we switched at the metal insulator transition, 2 times we didn't. If intentionally we did put thermal gradients, even by having a laser beam or by doing rapid quench, it's other way around. We didn't switch, so we pinned 8 times and we switched 1. So it's not 100%, but I would say it's pretty controlled, so to say, process. Okay, then the other thing that we try to do is to apply some torque. Because, I mean, I know it sounds a little bit oversimplifying the problem, but if you have got this chiral state, you would like kind of try to move it, even apply a torque in one way or in another way. And so we say, let's see if this happens, if this can be done. And when we did this, in the nearly commensurate phase, so in a already chiral phase, we didn't see anything. Why? Because before we can apply enough torque, we basically start to break the sample. These are layered materials, so they peel off very easily. So we had already to basically mount the sample on a Scotch tape, and then we give a torque with some very primitive wave, just by preloaded spring. Before you can change the chirality, you break everything. So what we decided to do is instead to not do the torque here, but first anneal to the incommensurate phase that is not chiral, and then cool down under a torque. And then we said, in that case, maybe it can work. And the idea is indeed that you go in this incommensurate phase, and then even applying clockwise on anti-clockwise torque, you go here or here. And indeed, it did work. We tried with photo emission, and we did see that there is clearly, so to say, a chirality signature for the alpha state if we give a clockwise torque. And if we do reverse the torque, we do reverse the chirality signature. So it does work. This is kind of, so to say, an interesting experiment, but it was not the full proof because we couldn't do the annealing and measuring in the UHV because there is a Scotch tape here. We cannot go up to 360 Kelvin and still have a good surface. So we had to cleave again every time. So we decided to do some also Raman to be sure that this is what's going on. So the Raman contrast, this is micro Raman, the Raman contrast is pretty high, And at the beginning here you have indeed two domains, 2 and 1 with different chirality. If you applied counterclockwise torque and you do a annealing cycle, you always stay in beta, and if you reverse the torque direction, you always, and apply annealing cycle, so you always stay in alpha. So this also tells you that by external torque, you can control this chirality. So our thing is, can this chirality be changed by laser pulse, strong laser pulse? So I would say the answer is yes and no for the moment. There is this nice paper in New Gedik group in which they did see that if you have got here some domains of alpha and beta, at the frontier of these domains, by laser pulse, you can write, so to say, probably smaller domains in this yellow region in which you have got the two chiralities. I would say the most impressive results that I also don't understand completely is this one, but is clearly not doubtful from the experimental point of view. What this guy could do is to create a domain wall between different chiral, so to say, configuration. And so this is Raman contrast. I showed you Raman is very powerful here, micro Raman. And what they did is to send a current here, and they can move this domain wall, switching this part of the sample in between the two lead, completely between one chirality to the other one. And they can go back and forth as much as they want. Okay, so this is about it for the chirality. And now we go to, so to say, the Mott versus Spires in this kind of compound. So these are very old data in which I show you, or in this color scale it's not very clear, but when you are in this nearly commensurate phase that is metallic, you have got a band that crosses the Fermi level. When you cool down, you do get a gap opening here, and indeed this corresponds to the metal insulator transition that you have seen in resistivity. So if you do electron counting here, and you think about one monolayer, you would say that in these bands there are 6 electrons, here there are 6 electrons, in the upper one there should be 1 electron. So the only way how this alphyl system could become an insulator would be by doing a Mott transition. And this has been the main, so to say, driving idea for a long time, until it has been shown that actually there is some dimerization. So this is not the first paper showing dimerization, but this is probably very straightforward to interpret. So you just do, in this case, diffraction along the C-axis, and when you are in the C phase, you clearly see 0.07 divided by 2 peak appearing. So clearly, no doubt, there is dimerization in the C phase. Another question is always the same. Is it Mott physics relevant, or is this dimerization that does make the job of making the sample insulator? So this was, I think, an important experiment that we have done that is kind of a likely one. Everyone always measured the commensurate phase with p-polarization. And what you do see when you do p-polarization and you are just weakly photoexcited, so here we have to increase the signal by 8, so we are a little bit out of equilibrium, we're weakly photoexcited, and we are transiently occupying states above the Fermi. So if you do it with p-polarization, which has been always done by us and by every other groups before, you do see this, what we call the lower Hubbard band, whatever it is, and it is, and you do see nothing above the Fermi. Basically, completely flooded by incoherent spectral weight that has no shape, nothing. And when you change the polarization from P to S, a new world appears. And you see here that now the spectral weight of the lower Hubbard band is strongly suppressed, and you start to see much more here above the Fermi level. Yeah, okay. Good. Now, the first thing I wanted to say is that due to the fact that this band and this band have got different polarization dependence, extremely different polarization dependence, a simple Mott model where you have an orbital that's split in two because of Coulomb interactions can be excluded. Because you would have the same polarization dependence here, and here clearly is not. So at least you have to include many orbitals. First point. Second point is the gap that we get is 0.15, and now the question is, could this be simply the bonding anti-bonding state of a dimer, of a dimerized out-of-plane state? And here we really needed to have some, so to say, DFT calculations done in a group of Angel Rubio trying to say us what's going on. And what they see is that if you have got dimers, just without correlations, you start here. Then you ramp up the correlations. This is what the self-consistent U for the cluster that they found, you would get here. If you have got a structure that is not dimerized, actually, you know that if you have got even dimers, we are very surface sensitive, so we may have two different surface termination, one behaving more like this, the other one behaving more like the red. You may have 0, 0, you should have 0, 0, 0 here because you are basically not dimerized, you are half-filled, up to a point where U is large enough in order to open a gap. So I would say simply that if you have no correlations and we have got a mixture of these two terminations, we should have a gap between 0 and 0.09. If you have got a mixture of these two terminations and you include the correlations, these are the correlations basically that they calculate self-consistent with constrained RPA. We should have a gap that is somewhere here, which is what we see. So our data suggests that correlations are there and should be taken into account. And then I will go very fast here. What happens at the last is what happens when you really see the collapse of the states. Now that we can see the dispersion so well, we can tell you something new. We can tell you that here the dispersion afterwards is really erased. So you get to a flat band. So gets flatter and flatter, and the states get nearer to the Fermi level. So while you are collapsing the band, you are basically localizing the electrons. It's kind of it's not so surprising. It's kind of an Anderson localization, but it's not disorder that does basically that breaks the shape of a wave function. It's charge density wave fluctuations. So how do they localize? They localize typically on the length of a David stars. It's 1/nanometer here, the scale, which means 1 nanometer is a David star. Okay, and here I go a little bit faster because I don't have time. I want just to say that this may be also relevant as a precursor phase to the nice results that have been observed in Dragan groups, where they could kind of even go to a glassy, so to say, mosaic phase where you have got these metallic domains forming, and that probably Dragan is going to speak about later on. Okay, so this is just I don't have the time for this. I just want to thank the people who contributed. So from my group, Weyan Kui, Jingwei Don, Gwenole Utrecht, Stefano Ponzoni, Yanis Laplace, and Roman Grasset. The Raman done by Yann Gallet and Alexandre Alekin together with us, of course. Support from the beamline scientist of Soleil, that's Dean Benouda. Samples from Laurent Cadio. Calculations especially of a unit cell by Alberto Zobelli, and other calculations with correlations from Angel Rubio group and together with Don Binchin. Thank you very much.